Okay, great. Thank you. All right. I guess with that being said, nah, did I have this? Yeah. So with that being said, thank you all for calling in. So today we've got one more item of our irregular Einstein Toolkit seminar series, where we ask persons to present on their recent research, maybe related to the Einstein Toolkit. These are typically more open-ended and less informal talks than you would have at a conference. We try to encourage technical discussions, and this is really just a general chat for things that might be interesting for the community. So today, we're happy to have Adam Peterson present his work okay, I'll read your title, Symbolic Code Generation for Tensorial Partial Differential Equations with Applications to Black Holes, Cosmic Strings, and Quantum Fields. So in particular for us of interest is that Adam actually implemented these things on top of the AMReX code, which is the basis for the new Carpet X driver. And among these things, there's also a BSSN set of equations that were used to evolve black holes. But this is mostly something where we want to see how to use AMReX in this particular scheme for a physical system that we care about. So Adam is working at Lawrence Berkeley Lab, which is one of the main sites for AMReX development. So he has hopefully insider knowledge about how this thing works on the inside. And with that, I'll hand it over to Adam. Please go ahead.
Yeah, thanks, Roland. Thanks for the introduction, and thank you for inviting me. Yeah, so I'm going to present my work on developing a code generator for the AMReX architecture. That's when I was first hired by Anne Altengren in the CCSE group at LBL, she mentioned that they wanted to develop a space-time solver in the AMReX architecture. And my immediate conclusion was, well, I can't do that. That's a lot of work, you know. And we kind of discovered that the best way forward was to actually develop, make the computer do this sort of code development for us. And then it kind of quickly snowballed into something even bigger than just, Einstein solvers. We've gone beyond, your typical black hole simulations, and we've started to work with more exotic objects like cosmic strings, which I'll talk a little bit about. And if we get to it, I'll go into even further into the exotic and talk about lattice quantum field theory, which is kind of the new project we're working on. Okay, so well, let's talk a little bit about the motivation. Well, you all are familiar with the Einstein toolkit. You know that high performance computing has generated new avenues of research for theoretical physics. And specifically for highly nonlinear coupled systems, we determined that we need to bridge the gap between the very pretty symbolic formulations and the equivalent computer compilable expressions. And of course, the examples of GR and quantum field theory come to mind. Oh, and I should mention, please stop me at any point if you have a technical question or whatever. I'm happy. We'll go as far as we can. I've made many more slides than probably is necessary, but so we'll just get as far as we can. So please stop me if you have a pressing question. Anywho, so how do we bridge this gap? Well, code generation is the key. So let's talk about, the most prototypical example. Let's talk about Einstein's equation. So Einstein's equation in symbolic form is, it looks very innocuous. It looks very simple. And that's, of course, by design. All the physics is contained in a very compact symbolic form, and it highlights the overall conceptual simplicity of gravitation as a space-time curvature due to the matter and energy distribution. Indeed, you can prove that this is the only equation that's compatible with the that's mathematically consistent, a way to couple the curvature of a space-time manifold with the energy matter distribution. So it looks very simple, of course. So what can we do with it? Well, we need to build a computational tool to solve Einstein's equation using, explicit time integration. We want massively parallelizable data structures and iterators for mesh data, adaptive mesh refinement, higher order time integrators, And we need a compilable expression for the equations of motion using higher order spatial discretizations. A lot of people are familiar, of course, that in order to do Einstein's equations, you need, at least fourth or even eighth order finite differencing in the equations of motion. So, is there a question? No. Okay. So parallelizable data structures, all of this AMR and subcycling and high order time integrators are all provided in things like AMReX and the and FlashX with immediate support for large scale problems with CPU and GPU accessibility. So we just need to write the equations of motion in compilable expressions without making typos or undetectable errors in indexing or finite differencing. Well, of course, let me take the example I was working on before I was hired at LBL. I was working on holographic superconductors, and the simple explanation of those is it turns out there is a correspondence between the quantum field theory of a superconductor and the an equivalent classical Einstein space-time system. Well, if you actually take your assumed form of the metric and expand it into the Einstein curvature tensor, you get this horrendous mess. And it just keeps going forever and ever. So indexing for something like that becomes extremely impractical right off the bat. You tell me the grad student who you're going to, say, take each one of these, take each X, take each Y, and put it into put it into a data structure, put it into a form that, something that can be compiled in C++ or Fortran. Good luck. Well, it turns out, of course, that there are packages that do this for many space-time solvers. Obviously, I'm talking to the Einstein Toolkit group that do these sorts of things for black holes, neutrons, stars, etc. But what about more exotic cases, cosmic strings, or a completely unrelated case, say lattice field theory, which has its own host of highly coupled nonlinear equations that are impractical to index by hand? So we need a better method for automating the translation of symbolic expressions to executable C or Fortran code. So let's talk about the anatomy of a partial differential equation solver. You have of course, the architecture of the high performance computing with block structured AMR, parallel data structures, internode communication, etc., that come from AMReX and FlashX. You have your actual PD solver that's built on top of it, which needs methods for declaration of data, initializing data, and advancing levels, and logic for refining, etc. And then you also have, say your actual system that comes out of a textbook, the evolution equations, say the Z4C, for example, that you would like to translate into, your PDE solver. Well, so you want a method where you can more or less read off the expressions in the textbook and be reasonably certain that you haven't made any sort of typos in the indexing, for example. So code generation is the way forward here. It's a method for discretizing symbolic equations and converting symbolic expressions to C or Fortran, for example. So what are some of the things we want out of our code generator? Well, we want things like the specification of finite difference ordering, stenciling, dimensionality, etc. as inputs, which CodeGen can automatically expand into correct compilable expressions. So we also wanted to have objects like a metric-induced connection where you simply tell it, okay, here's my metric, write for me the Christoffel symbols, for example, write for me the Riemann tensor, say for reasonable versions of the energy momentum tensor, can you expand those for me and put those into compilable expressions? Finally, we want syntaxing to be sufficiently versatile to easily write code in many different languages. So we originally wrote this code generator to do things with AMReX, but it quickly became, quickly became of interest to other groups. Like, hey, can we do this for, say, FlashX, which unfortunately, for me at least, is written in Fortran and not C. I knew C. I did not know Fortran at the time, so I needed something to kind of do that for me. So So we use CodeGen to, of course, translate Python expressions to C++. So a little bit deeper as to what that means. Well, the actual C++ code is going to contain things like four-dimensional arrays that contain the actual physical field data indexed, by three-dimensional grid points, and say a fourth index, since we have multiple fields that we'd like to put in our system. We have a field variable, say psi, is contained in an object like an array with the three indices for the spatial location, I, J, K, and of course the fourth index telling us which field we're actually talking about. We would like our code generator to be able to say, okay, I want the partial derivative of u, for example, give it to me in central finite differencing to say second order here, and it immediately spits out the actual compilable expression. And then, finally, if you're trying to write out things like the Riemann tensor, for example, or say the Ricci scalar from the Ricci tensor, for example, you'd like your code generator to be able to take the actual simplified expressions for tensor manipulation and actually expand those out into actual compilable code. So while we were doing this, we kind of realized that a code generator needs, the objects that you need for your code generator, or what we call a symbolic object, needs three pieces of information. You need a symbol that tells you what you're talking about. Okay, this is the psi field, this is the pi field, this is the u, v, w field, etc. You need it to know how to reference that, or you need to know what that symbol is actually referencing. In this case, it's referencing, say, an array of, like we talked about previously, of indexed objects, I, J, K, and the field you're talking about. And finally, you need it to contain an expression. So, for example, the Riemann tensor is not its own self-contained object. It's defined in terms of the metric, covariant derivatives, Christoffel symbols, etc. You need to be able to reference that expression in your code generator. So what does that look like? Well, let's take the very simple example of the kind of an early version of the code generator we wrote. Here I'm taking a simple case of, I'm declaring two symbolic objects, u and v. And I would like v to contain some expression that's determined in terms of u. So for example, v is equal to u squared plus the Laplacian of u. This is some exotic form of a Poisson equation, for example. And I would like to be able to reference this information in various forms. I'd like to be able to say, well, I want the symbol to be set equal to this expression, or I want the array object to be set equal to this expression. And so I can reference all three of these pieces of information: the symbol, the array object, and the expression it contains. I should have those readily accessible. And then finally, the actual code generation part should be able to make statements like v is equal to the array object that it's referencing. It's equal to the equation that it contains. And so there's various forms that you can spit out. So for example, in our AMReX version of the code generator, we have various outputs that we can generate. Say I want to define a symbol v equal to the expression that it contains. So if I say AMReX sim to expression, it actually spits out an AMReX real object. V is equal to the expression. I can set it equal to the index expression, or I can set the indexed expression equal to the equation I've put inside of it. Additionally, we for automating things like differential objects, we want our code generator to be able to do that as well. I want to be able to take a symbolic object and tell it, I want the first derivative to fourth order accuracy with central finite differencing, for example. I should be able to just say, take the derivative of this, spit out the expression that it contains, and I should be able to automatically generate this information. So once again, for the case of the AMReX code generator, we have our, we say want to take the derivative of the object psi, which in our case, psi is a, I guess psi is just a scalar in this case. And so it automatically spits out all of the derivatives in the number of dimensions we're considering. In this case, it's just 2. And so you can see it automatically spits out the fourth order central finite different expressions for these differentials of psi. So finally, we want to put this all together into, say, solving something like the Klein-Gordon equation. This is just an example. Obviously, the Klein-Gordon equation is much simpler than the things you'd actually want to use this for. But let's take it just, just as an example to get a feel for what's going on. So the Klein-Gordon equation in first order form in first order time advancing contains 2 variables. It contains the object psi and the conjugate momentum. So I should be able to take these equations of motion here and just more or less read them off. I want to say the right-hand side of psi is equal to pi, and the right-hand side of pi is equal to the Laplacian of psi minus the mass squared of psi. So as you can see here, that's more or less what I've written down. I've taken the, I say, okay, I want the second derivative of psi in both the x direction and the y direction. I want to take the subtract off the mass squared times psi, and I should be able to say, okay, now print out the right-hand sides of these expressions here. And of course, if I do that, it actually prints it into a nice compilable form that I can more or less copy and paste into whatever kernel I'm working with.
Adam, one
yes.
question on your previous slide. So I noticed that when you assign to the psi expression, you use an equal sign, but for the pi expression, you have plus equals. Is that just a typo, or is there any deeper meaning to that?
Oh, there's no deeper meaning to it. The expressions are by default set to 0. Okay. So that'll be explained in the next slide. In this particular case, that's unnecessary. You don't need the plus equals here. It's for, the Klein-Gordon equation is overly simplified, but let's say you have an actual tensor equation of motion, for example, that you might want to index in I and J, for example, then the plus equals becomes useful. But no, there's no deeper meaning here in this particular case. So of course, for the Klein-Gordon equation, this is all overkill. Anyone can write a wave equation solver very easily if they know just a little bit of coding. But what about the Z4C formulation of Einstein's equations? Can it handle something like that? So let's take the example of the right-hand side expression for the traceless extrinsic curvature. Well, I want to be able to take this expression, this chi times this bracketed expression plus alpha bracket plus all this additional information. I want to be able to more or less read these off. This is the textbook expression here. I want to read these off, and I want the code generator to handle all of the expanding, the indexing, and the finite differencing. So let's see how that works. So very similar to the previous case, I have defined an object called the right-hand side of A tilde. Sub LL means it's a two lower indexed tensor. And I'd like to fill its expression with the actual equation of motion here. So you can see, this is a lot, but the idea here is I have more or less been able to take this expression here and read off the various objects. I've read off chi. I've defined previously a covariant double derivative of alpha, trace-free version, alpha times sim times the trace-free Ricci tensor, et cetera, et cetera. And you can see that this is, each of these terms is a read-off version of these actual textbooks expressions. So this, hopefully would cut down on typos and errors in coding. And finally, I can spit it out. I can say, tell me what the right-hand side is. It automatically knows it's a 2-index tensor, so it needs to spit out 6 components. So it knows it's a symmetric 2-index tensor, but there are 6 independent components. And it actually, it takes all of this information and it knows what this means. It actually spits out the actual compilable expression that I'd want to reference in any sort of time integrator. So we took this to extreme. We wrote out the entire Z4C system. We wrote out the entire initial data generator. We essentially had the code generator build an entire solver for us. And we ran it on Cori, and yeah, so this black hole merger, we've all seen them before, but this one was produced entirely from a code that was generated from the code generator. With very minimal specification. We gave it the initial masses, we gave it the initial separations, momenta, we specified some of the internal parameters, eta, kappa 1, kappa 2, etc. And it produces this very nice picture, which, so somewhat qualitatively, we can compare it to the actual LIGO signals versus our own signals, and you see it very qualitatively agrees quite nicely with the expected waveform of a black hole merger. We can, of course, be a little bit more quantitative with this. So this is the example of the waveform we get for just a simple head-on collision. We see it matches up quite nicely with previous groups' work. Of course, we checked all the convergence testing associated with these waveforms, and indeed they are all consistent to, in this case, to second order, due to even though the system is fourth order finite difference. When you extract the signal, you need to interpolate onto the sphere, for example, from Cartesian data, and that reduces your accuracy from fourth order to second order. So finally, for to be really qualitative here, we did the simple testing for gauge waves, and we see on the left here just an image of what the gauge wave looks like after 1,000 iterations, or excuse me, 1,000 light cone crossings of increasing resolution on the grid. And we can, of course, do we can, of course, make this quantitative by looking at the norms of the differences between the two, between various resolutions, and we see that we do get, indeed, fourth order convergence in our system. At least for early times. Of course, it degrades as you get further out in light crossing times. Okay, so this has all been done before. Of course, the Einstein toolkit is perfectly capable of handling all of this. But we wanted to take this, once we got this working in AMReX, we started to ask questions like, well, what's something that hasn't been done in the community? And one of my colleagues down in Chile started asking, well, there's this interest in cosmic strings and the waveforms of cosmic strings, in the hopes that we can somehow detect some dark matter candidates through the waveforms that we'd see in LIGO due to the collisions and collapsing of cosmic strings. So we said, okay, so let's see if we can do that. Can we make our code generator handle a problem like this? Excuse me. So the problem of cosmic string is, of course, a little bit more involved in a black hole system. We wanted it to have internal currents so that it would actually hold its form for a large amount of time. And we wanted to ask, can the code generator be of use? So the problem, of course, is that with internal currents, the initial data becomes a little bit more complicated, since you cannot ignore the momentum constraint anymore. You actually do need to solve it in addition to the Hamiltonian constraint. And we also now have matter sources with energy and momentum in the evolution equations as well. So we need to be able to handle those. So just to be a little bit more quantitative here, the system we're solving is, of course, the Einstein's equation. We have a Higgs field that couples to the electromagnetic field. And then we have an additional field, sigma, that carries the current inside of our cosmic string. And that's expressed by saying an nonsense for the initial data of sigma is equal to some profile in the radius and theta times, excuse me, the times the e to the I omega t minus m phi. That m should actually have an r, should be an m over r for the radius of the initial radius of the string. So all of this means is now the initial data involve both energy density and angular momentum terms that we need to solve for. In addition to our evolution C4C equations, we now have evolution equations for phi, sigma, their conjugate momenta, and the electromagnetic field. So again, this is another complicated system that's indexing and expanding in actual compilable code would be an absolute nightmare. And so we want our code generator to be able to take these expressions and produce for us compilable expressions. So let's take the example of the most complicated case here, probably the evolution of the electric field, for example. It's written in all of these. Some of these, make sense. Some of them are just partial differential or partial derivatives, but we also have covariant derivatives in the conformal metric. I guess that's as complicated as it gets, but still, we want to be able
do you need to prove the well-posedness for the system first, or you just try it away?
So the well-posedness of, okay, quick answer, we personally did not prove it. There are other groups that have done the well-posedness of these systems. So the well-posedness of the matter fields is almost trivial. It's more or less just a wave equation, or maybe a nonlinear Klein-Gordon equation written in 3+1 form on a curved spacetime. So that one's already well posed. Very similar for the ENM case. If you take the ENM, if you take a well-posed version in flat spacetime, you are more or less guaranteed that it will be well posed, or at least the electromagnetic part will be well posed in a curved spacetime. So as long as all three of those are individually well posed, the system together should be well posed. Okay. No, I emphasize we did not do that. We simply pulled these equations from other groups that had had developed that had developed these field equations in general for other problems. Indeed, there are other groups that had done cosmic strings before our addition was this internal current that makes the initial data a little bit more tricky to solve. So we knew that they were well posed. We knew that they would generate a stable system. Okay, so you can take these equations, you can do the same thing you did before with the symbolic versions. You read them off from your expressions that you get out of paper or you derive yourself, and you have it spit them out. And so this is the X component of the electric field, right-hand side. As you can see, it's very involved even before you expand out things like covariant derivatives, etc. So this makes it clear that doing things in this way, where you can actually just read the tensor expressions out of a textbook, have the code generator do all the expansions, it becomes very clear that this is the way to do things to avoid making undetectable typos and errors, things that the compiler would not see, but would lead to incorrect results, would lead to unstable evolution, and you would have very difficult time trying to find out how many mistakes there were, where the mistakes were, etc. So finally, does it work? So again, this is a system we developed entirely within our code generator. We had it write out all of the AMReX code, and we tested it out. So this particular case is the case where we the wave number initially of our field is 2, so it's got 2 nodes. Of the sigma field around the cosmic string here. Oops. And we see that it has a nice rotational evolution. We see that it begins to collapse. Part of the string, the one that's associated with phi, actually collapses into a black hole, but what we see here is that the part associated with the internal current actually gets blown off and ejected. So this is previously unpublished result. This is something. So this is kind of early work, of course, but this is kind of an exciting. We see that this is going to lead to some interesting physics. How does the internal current affect the collapse of a string into a black hole? Does it prevent the collapse? Does the string always blow off the current? There's lots of questions here that we can now approach that became accessible to us within a matter of days rather than months it would take to actually develop something like this from scratch. We've already done things like extracted the waveforms for a cosmic string collapse, for example. In this case, we see both the L equals 2, M equals 0 spherical harmonics of the waveforms here. There's not a whole lot to see from this case other than it's a unique waveform compared to those of head-on colliding black holes. But our goal will be to test various cases, test various values of M and omega to see what does it do. Does a larger M, for example, does it, it should mitigate the signal, it should elongate the signal, we expect, since the string will collapse much more slowly, much more smoothly. So that's kind of where we are with this project at the moment. But I just wanted to illustrate, problems like this are now accessible within AMReX with our code generator in a matter of hours or days instead of the weeks you'd have to do doing a lot of boring indexing, etc. for making the code from scratch. So just to summarize, code generation allows us to build a fully functional space-time solver in C++ using symbolic manipulation in Python, SymPy, or Mathematica. It effectively bridges the gap between symbolic textbook expressions and equivalent numerical code. We've made it sufficiently versatile to be made compatible with other architectures based on C or Fortran. I mentioned that we developed an equivalent space-time solver in FlashX with very minimal changes to our code generator. It was a matter of telling it to spit out Fortran in the correct syntax instead of C code for AMReX. I don't have the examples in front of me right now, but we did test in it with the gauge wave, and it was consistent with the finite differencing we had set for it. So, and with this example for cosmic strings, it becomes clear that code generation is more than a single application. It's we see it as a method for future high performance computing development. So I'm going to stop there and open up for discussion. If there aren't too many questions, maybe I'll talk a little bit more about the other project we're working on, which is the quantum field theory problem. But I didn't want to do that unless people want me to, essentially. So
I think there might be questions. Let's see.
Yeah,
if somebody would speak up if you had questions. I saw one hand up for a second.
Well, I was wondering, you didn't mention, are you using the GPU capability of AMReX in your application?
Yes, we have done that.
Okay.
Especially for the cosmic strings, we ran it on Perlmutter's GPUs.
I'm also wondering, do you have any examples so far of a cosmic string that doesn't collapse?
No, not yet. Presumably, if you make the angular momentum large enough, it should prevent the collapse.
Right.
So I didn't want to oversell because this is very early on.
Sure.
We've done this one example. We were very happy that it didn't. We were just happy it didn't crash.
I understand.
We were happy that it produced a wave signal that looks like other previous work on cosmic strings that do not include these internal currents. So that's all work to be done. That's work that's what we're moving into. So this talk, I didn't originally want to present on the cosmic strings because it was too early on, but we got this result. I think got this result in the past week or something. I was like, hey, that's pretty neat video. Let's put that in. Let's show off a little bit. So that's what that is. It's not quantitative other than the waveform. But yeah, you're right. Presumably, if you increase M large enough, it should prevent black hole formation.
Okay. Then Liwei, you had your hand up next.
Hi. First, the cosmic string evolution is pretty cool. So I want to ask if you only use the code generation to produce the right-hand side of the equation only, or you also use it to set up some other setup of the code?
So we short answer, yes, we used it for both the right hands code as well as things like ensuring constraint, ensuring that the our gamma tilde, our conformal metric remains determinant equals 1.
So sorry, my question is, did you use that, say, to generate the loop, say for, also it generated, say, for loop also, the declaration of the for loop, instead of just the real equation expression?
What do you mean by the for loop? Like,
say you go over all the grid point, you will need for
I
equals something that for those things. Are you also generating with code generation? Or?
For this particular example, no. We took this out of a standard PDE solver in AMReX, kind of stripped all of its content, and then everything that's generated in the code generator is something that you copy and paste into the for loop.
I see.
Yeah.
Okay, thank you.
Okay, Samuel, you're next.
Yeah, thanks. No, I just had a question with regards, well, sort of double-edged question. But the first question with regards to scaling, right? Like in these sorts of, I guess, goes along with Louis' remark in that I would say the nuts and bolts is really being done by hand with regards to the infrastructure, and the code generation is really just the, like you said, the right-hand side. So I would say is it true that the technical aspects of the actual evolution framework is still written by hand, and it's really just the application codes that are done with the code generation?
At this point, we took the actual time integration, we took that out of previous kernels written in AMReX. We want to develop it such that that is something we want. So this is still a little bit in development. We want to make it modular. We want to be able to say, we want to include this kind of time integration. We want to include this kind of stenciling. And then the code generator automatically knows to include those statements in the initialization process. So again, short answer, no, not yet. Long answer, we want it to. That is, yeah.
And so for the, I should say, for the setup that you have right now, have you tested the scaling aspects of it?
We did a little bit of weak scaling early on. So this was done mostly by Don Wilcox, and it scales very nicely. I don't have the slide in front of me, unfortunately, and we didn't include it in the paper since it was kind of early on, and we were originally going to do some actual quantitative scaling testing, but we are actually going to save that for our next paper that will actually include the cosmic string. So again, short answer, yes, it scales nicely. Long answer, you have to wait for the a more quantitative answer.
Okay, thanks.
Thank you. Wolfgang, you're next in line.
Yeah, can you hear me, or is the audio crapping out again?
It's good.
Okay, perfect. So my question is that it seems that this is focused mainly on correctness and ease of use, but I was wondering, should also be a very good place for high-level optimizations. If you have like the complete call, basically tree of expressions you have in one place in a high-level language, one could do something like eliminating common sub-expressions or creating temporaries that are used in, from those and stuff like this. Also using things like symmetries of matrices or Christoffel symbols or Riemann tensors or whatever. Yep. Is this also built in, or is this even a goal of that?
Some of it is, yes. So the example earlier, I showed the building of the right-hand side of the traceless extrinsic curvature tensor, which is a symmetric 3x3 tensor. So we contain that in this expression here. We say it's symmetric in the index 0, or in the first and the second index 0 and 1. And it automatically knows that it only needs to fill those 6 independent components. So when you actually spit out the right-hand side, it doesn't spit out 9 components, it spits out 6. And we have things built in for anti-symmetric tensors. In that case, if I were to tell it was an anti-symmetric tensor, it would only spit out 3 components. you can mix and match symmetries between different indices. So for the Riemann tensor, for example, the first two indices are antisymmetric, the last two indices are antisymmetric, and it knows that it's only going to need to spit out I don't know if it doesn't know about all of the symmetries of the Riemann tensor, but it does know that it only needs to spit out, not 3 to the 4th components. It only needs to spit out, is it 6? Something like that. So some of that is built in. As for common expression elimination, that's not contained in there yet. So yeah, it is. There is some built-in simplifications like that, but it's not. So another example is you see that it knows about the knows to put a standard power expression. Most of the time, it's easier for it to actually spit out if it's an integer power. Compilers running codes is much faster if you actually spit out just the expanded version of those. It knows how to do that, to identify those. But we haven't included anything for actually, common expression elimination yet.
I'm asking because that could potentially speed up this a lot. In particular, if you have so many expressions that might even share
That's right.
different right-hand sides. For example, there's a library for Python called numEx and similar things that do that, and they have pretty impressive advertisement numbers. And I mean, at some point, it doesn't even have to do anything with tensors or vectors. It's basically you have a list of arrays that correspond to your different components and a bunch of expressions that connect them. So it's basically like a tree, and basically a graph, a call graph, and this could be manipulated in a much cleaner way than dealing with tensors and so on, because having to know all these symmetries, that is tedious because it's on the low level, but this sort of optimization would be on the highest level.
Yes, you're absolutely right. This is something we are aware of, and we do want to include it. We're just not there yet.
All right.
Okay, Zach, I think you get the last question most likely. Go ahead.
Sure. Hey, Adam.
Hi, Zach.
Yeah, I was absolutely thrilled to see the paper hit the archive. It's wonderful to hear that you folks are making excellent progress on the code generation front with AMReX. It's awesome. So I just wanted to throw out a couple of pointers. First, the common subexpression elimination algorithm in SymPy is elegant. It's amazing. It does a great job, and it's efficient. Highly recommended. When you get a chance to get to that with the AMReX code gen, highly recommended. I think you'll find it's very nice. Also, NeRPy has it actually rebuilds the expression tree. It goes beyond what SymPy CSE does by default, and attempts to optimize a bit further, finding more common subexpressions. I mean, you can look at sometimes when you look at the SymPy CSE output, common subexpression elimination output, you'll see that it didn't quite get all the find all the patterns that the human eye might catch, and so by all means, I mean, NeRPy is permissively licensed for a reason. Take a look if you like.
And by the way, a lot of the code generation was based off the NeRPy. We use that as an example to build our own. So, as you're probably aware. So yeah.
Wonderful. Well, imitation is a sincerest form of flattery, right? So wonderful. I appreciate that that NeRPy was useful in this regard. I'll also just say one last thing in terms of CPU-based kernels. single instruction, multiple data, the vectors, the short vectors that you can leverage to accelerate computations on numerical grids. We also have a nice SIMD code gen as well, and it tries very hard to find as many, for example, fuse, multiply, adds, fuse, multiply, subtracts, etc., to optimize the kernels even more, because compilers. I mean, it's funny because I've given multiple talks on NeRPy, and someone in the common questions are, why don't you just let the compiler do the CSC? Why don't you just let the compiler do the SIMD? And the answer is, it was a question. Have you ever tried solving Einstein's equations before? Have you ever seen how complex they are? Have you ever seen how a compiler chokes sometimes? How many bugs has the Einstein toolkit uncovered in compilers because we saw the Einstein's equations and no one else has expressions quite as complex as ours? So, right. So yeah, that's just a couple of ideas that you might want to consider, and by all means, reach out if you have any questions.
I was just gonna say it might be nice for us to actually have a chat, look at it more closely, get the true experts' take on this, and yeah, I would absolutely like to set up a personal talk with
absolutely,
you.
Yeah.
Yep. Much appreciated.
Yeah, just reach out, and we can schedule something. I'd love to chat. I've learned a lot just by bumping my head as I walk around in the dark. So
yeah, that's yeah, I understand that.
Anyway, again, a wonderful talk, Adam. Thanks.
Thanks, Zach. Appreciate it.
Right, thank you. I guess there are no more questions, at least right now. So with this, I think we're at the end of the presentation. I guess two things that I would probably want to suggest. So Adam, I guess you'd be happy if people were to contact you afterwards with questions via email?
Yep.
And then the other thing, there is a code available on your GitHub repository for StayVR, if I remember the name correctly, and that's basically the implementation for BSSN based on your code generator, or is there something else that I should, for example, link on the seminar page?
Let me look up the latest version. Let me send you a link, and then you can post that, because there have been a few iterations. We abandoned the BSSN in favor of the Z4C and the CCZ4 most recently. So I will send you. I need to look up exactly what the current link is, and I will send that to you, and then you can post it.
Yep, because it seems quite impressive, and in particular, if nothing else, if somebody wanted to get quickly started using AMReX, I think this is also a very good way of trying things out, because you kind of have working examples, and then you can get the code generation to work, and that hopefully helps a lot.
Yes, perfect.
Yep, thank you. So with this, thank you very much for an interesting talk. Thank all the participants for the interesting questions.